सर ये अलाइंड एंड अनअलाइंड मेमोरी एक्सेस ये था बुक में 1.4.3, इसको भी एक्सप्लेन कर दें।
इसके बारे में डिस्कशन आज के लेक्चर में होगी।
ओके सर।
So मैं एक बार रिवाइज कर देता हूँ. Let's have a brief overview of the last lecture. In the last lecture, we started off chapter number 2 of your textbook, and it had the title of Cortex M architecture. So we are going to discuss the Cortex M architecture based on the following contents. We will have a brief introduction and a history of Cortex M architecture. Then we will start the microprocessor architecture, which is the most important part of your microcontroller. And within this microprocessor architecture, we will discuss the assembly set, instruction set of the ARM architecture, its register sets, its processor modes, and its different control sequences. Then we will discuss the data path and the address mapping. Then we will discuss the NVIC, which is also called Nested Vector Interrupt Control, and the bus matrix system, and memory and peripheral devices. Started off with the family, we are going to discuss this particular family of Cortex M of ARM architecture, which include Cortex M3, M4, Cortex R4, and Cortex A8. This family is the latest one of all, and the word M, R, and A belongs to different family members. So Cortex ARM processors have different families. The first family is Cortex M profile family, yeah, Cortex M family in general words. These type of processor which belong to Cortex M family are used in microcontroller designing. Similarly, in Cortex A profile family members, they are used in the high performance application or mainly in cellular markets. And the Cortex R profile family, these microprocessors used in real world operating systems or real time applications. So those applications which include RTOS and real time programming, they include the Cortex R profile processors. Cortex A are used in cellular networks, and Cortex M used in microcontrollers. This is the main architecture of any general ARM-based microcontroller. In any ARM-based microcontroller, there will be a microprocessor core. It will have an NVIC. NVIC is Nested Vector Interrupt Controller, and it will be evoked only when an exception or an interrupt occurred. Whenever a hardware or software interrupt or exception will occur, the microprocessor will enable the NVIC. It will stop the current execution of the current application, and it will go to NVIC and ask it to resolve this error or resolve this exception. So this NVIC will be evoked. It will do something, and that something includes its handling process. And after handling that particular exception, it will resume the post task, which was the current task, and it will give the control back to microprocessor core again. It will have a bus system and a bus matrix. It will have memory, and it will have a mechanism to attach the peripheral devices, and it will have its own debug system. So these five are the main parts of any microcontroller which are based on ARM family. So this is the hierarchical block diagram as well. So you will have a microprocessor core, either Cortex M4 or Cortex M3. It will have the NVIC and a SysTick timer. It will have a debug interface. It will have its own bus matrix, and this bus matrix will be connecting your memory, peripheral devices, IOs, input, outputs, sensors, actuators, etc. with your microprocessor core. So this bus matrix will be responsible to read the memory, to write something in the memory, to read the sensors, to read the data. So these all things will belong to a bus matrix system. And this whole block has been developed by ARM itself, and the memories, peripherals, and IOs can be developed by ARM or any other chip manufacturer. This was the difference between Cortex M3 and Cortex M4. Cortex M3 include all the basic hierarchical or basic architecture, but if it has the extension of DSP instruction, then along with DSP instruction, it will be called as Cortex M4. So Cortex M4 is the latest of them, and it include all the features of Cortex M3 plus an extension of DSP instructions. And if the Cortex M4 will also have a GPU in it along with an ALU, that ALU will perform the arithmetic instructions. The floating point unit will perform the instructions on floating point numbers. So if it will have the extension of FPU included in it, then it will be called Cortex M4 architecture. So this is the difference between Cortex M4, Cortex M4F, and Cortex M3. The first part of microcontroller is its processor core. And the processor core that we will be discussing in this particular subject is Cortex M3 core. So the Cortex M3 core has the following parts. The first part is its instruction set architecture, which is called ISA. Then its register sets, its processor operating mode, its interrupt and processor reset sequences, its pipeline architecture and its data path, and also its memory address mapping. So starting from the very first part, which is instruction set architecture, the ARM-based microprocessor core corresponds to two different type of instruction sets. The first type of instruction set are called the ARM instruction sets. The second type is called thumb-based instruction set. In thumb-based instruction set, the instructions will be encoded into 16-bit machine code. Each assembly instruction will be encoded into 16-bit machine code. Whereas in ARM type of ISA, each type of instruction will be encoded into 32-bit instruction code. Whereas there is a broader or a superset of these ARM instruction and thumb instruction, which is also called thumb2 instruction set. In thumb2 instruction set, it include all the instructions of ARM and thumb ISA, and it will try to encode each instruction into 16-bit or either as a 32-bit. So many of the instructions will be encoded in 16-bit instruction, whereas a few of them will be encoded into 32-bit. In terms of execution performance or in terms of code density, we compared the ARM and thumb instructions as well. So ARM instruction set has a better execution performance. Whereas in thumb instructions, since each instruction is encoded into 16-bit, so it will have a higher code density. Whereas the thumb2 has the general better features of both ARM and thumb simultaneously. Thumb2 will have approximately 26% improvement in code density because a few of the instructions are from 32-bit instruction set, whereas many of the instructions are from the 16-bit instruction set. So it will have improvement in it will have an improvement in code density as compared to ARM, better performance as compared to thumb by 25%. So in terms of charts, we discussed these charts as well. So in terms of memory usage or code density, that was performing the best. ARM was the worst one, but the thumb2 was in between. So the thumb instruction set had the lowest, or you can say the highest, or it was consuming the lowest memory. Consuming the maximum memory, it will have a lower code density. Whereas the thumb2 is in between them. In terms of performance execution, ARM was best, thumb was the worst, but thumb2 was very much equivalent to ARM. After discussing the ISA, ARM-based microprocessor include all total 16 registers. Those 16 registers have been categorized into different types. Starting from R0 to R12, these 13 registers are called general purpose register. A general purpose register can hold any particular variable data or its address. So any address or any data can be stored inside these general purpose registers. Among general purpose registers, we have the R0 to R7. These registers are called the low registers. The low registers are the one which can be accessible as well as through ARM instructions. Whereas the high registers, which are starting from R8 to R12, these registers are only accessible through ARM instructions, and thumb instruction set cannot include these registers. So starting from R0 to R7, these are called the low registers, whereas others are called the high registers. The R13, R14, and R15, these are the special registers with a special name as well. So R13 has a special name called stack pointer. So it will always be used as a pointer to point the top of the stack. So ARM architecture or ARM processor supports two different stacks simultaneously. The one stack is called the main stack. The other is called the process stack. So it's a bank register basically. It will show you only one depending upon the control sequence, either pointing to the main stack pointer, or it will be pointing to the process stack pointer. Whereas the link register is a special register that will hold the return whenever an exception will occur, or the link register will hold the return address at which the current program will start the execute after the termination of the exception or interrupt or any function. Whereas the last one is the program counter. Program counter is the special register that will contain the address of the given instruction that is going to be executed. So the particular instruction that you are going to execute, the address of that instruction will be held by program counter. So program counter will be responsible to execute your program instruction by instruction based on the address stored in it. This was the main map. Starting from R0 to R7, these registers are called the general purpose low registers. From R8 to R12, these are the general purpose registers, but only be accessible through ARM instructions. R13 is a banked register. It will contain two copies, either from MSP or PSP, but only show one value at a time. R14 is a link register, and R15 was the program counter.
Excuse me, sir. सर जो R8 से R15 रजिस्टर्स हैं, आपने कहा कि ये खाली आर्म इंस्ट्रक्शंस से एक्सेस किए जाएं.
R8 से R12 की बात कर रहा हूँ. R8 से R12 तक जनरल पर्पस आर्म इंस्ट्रक्शन सिर्फ उसको एक्सेस कर सकती है.
सर उससे करेगा. चलिए सर, R8 से R12 सर आपने कहा थंब नहीं करेगा, लेकिन सर थंब 2 तो उसका ब्रॉडर सेट है, तो थंब 2 कैसे नहीं करेगा?
थंब 2 कर सकता है.
थंब 2 कर सकता है.
मैं जी थंब 2 तो सारे रजिस्टर्स को ही एक्सेस कर सकता है.
हाँ जी, क्योंकि वो ब्रॉडर है.
जी थंब 2 इज अ सुपरसेट ऑफ आर्म एज वेल एज थंब. तो थंब 2 कर सकता है. बस इसमें डिफरेंस ये आएगा कि ऐसी इंस्ट्रक्शन जिसमें ये सब इंक्लूडेड होंगे ना, R8 से R12 तक, उन सब इंस्ट्रक्शंस को थंब 2 32 बिट इंस्ट्रक्शन रीड करेगा.
ठीक है.
तो उन इंस्ट्रक्शंस को वो 32 बिट के तौर पे एनकोड कर देगा. लो रजिस्टर्स वाली इंस्ट्रक्शंस को वो 16 बिट के रजिस्टर के तौर पे एनकोड कर देगा.
ओके सर.
The next special register was a program status register. Program status register is basically a special register that contains a special information based on the current execution of your program. It will have three types in it. The first type is called the application program status register. It includes a few flags. Those flags will tell you the result of the execution of your current instruction. Once the instruction will be executed, and some arithmetic functions or some sort of any address handling or address mapping will be performed, the APSR may get updated based on the result presented by the ALU. So whenever the ALU will present the result, based on the value of that result, the APSR may get updated. So it includes total 5 enabled bits which are readable as well as writable, but the other bits are reserved for the future purposes. And each bit represent a flag. For example, bit 32 is representing the negative flag. Whenever the execution of your current instruction will give you a negative number, this negative flag will get updated. So if this negative flag is getting updated, it means you are telling the processor that the execution of the current program gives you a negative number. Similarly, bit number 30 is called the zero flag. Whenever the result of the current execution output will be 0, this zero flag will get updated. Similarly, the carry flag is the one which will be arised or which will be turned on whenever the result will produce an overflow, an unsigned overflow. And V is the signed overflow. Whenever you are using the signed numbers, those signed numbers, if they generate a overflow, the overflow flag will get updated. Similarly, the Q flag is also called the saturation flag. The second type of the program status register is called the IPSR. This IPSR holds the exception number. Now, exception number is the one we will see in a little while in chapter number 4, that we have developed a vector table. That vector table include all possible exceptions or interrupt that can arrive while the execution of your code of any program. So that vector table has modeled hierarchically all the possible exceptions and interrupts and given it a possible number. For example, the reset handler, whenever a process get reset, that type of reset type of exception has the exception number 0. Whenever a hardware fault will occur, the hard fault will have the exception number 1. Similarly, non-maskable interrupts, bus matrix interrupt, or ADC interrupt, or timer interrupt, all these interrupts have been given some exception number. So that exception number will be put inside these bits of IPSR, and it will tell the processor that we are going to execute this particular exception handler, and then we will resume the current programming task. The third type is called the EPSR, or also called execution program status register. It contains a very few bits which are readable as well as writable. All other bits are reserved. This bit IT bits are used to tell the processor if the instruction include the if else conditions, then those if else conditions decision execution will be done by the ICI or IT blocks. This IT block or IT bits will get enabled when if condition will be satisfied, or otherwise in else condition it will turn off. So it will tell the processor whether you need to execute the if condition or you need to execute the else condition. And this T is representing the thumb mode. If this T is turned on, the bit number 24 is a T bit. If this T bit is turned on, it means you are telling the processor we are in thumb mode. Otherwise, if it is 0, then you are telling the processor you are in ARM mode. So this T bit is a thumb bit. These bits are used for the if then instructions. Exception number will hold the exception number or the interrupt number from the vector table, and these flags will hold the results of the output of ALU. This is the description of all these bits: the negative flag 1, 0 flag, the interrupt continuation instruction or if then instruction, the thumb bit, and the exception number. And the last register that you are going to use in this ARM architecture is called the control register. The control register has only 2 bits enabled for readability and writability. All other 30 bits are reserved. And for those 2 bits, each bit has a different meaning. For example, if you are considering bit 1, in bit 1, if that bit is 0, it means you are using the main stack. So if the bit 1 is 0, it means you are currently using main stack, and the R13 will be pointing to the main stack. That is why it will be called MSP, main stack pointer. And if you will set this bit to 1, it means you are using the process stack, and R13 will be pointing to the process stack. That is why it will be called PSP. Whereas the control bit 0, it has a different meaning based on the mode or the privileged level. If your bit 0 is at 0, it means you are in privileged mode. In privileged mode, you have all the possible accesses. You can update any possible register. You can write any possible register. You can read from any possible register. So in privileged mode or in thread mode, this control bit will be 0, and you will have all the accesses inside your microprocessor core. And if this bit is 1, it means you have given an unprivileged or user level access, and you will have only limited access to limited registers. So this will be enabling the access level of the user program or the OS program. If this bit is 0, it means you have full access. And if this bit is 1, it means you have only partial access. And in parallel, we will be discussing the RISC-V architecture as well. RISC-V, as we have discussed earlier in the last lecture, that RISC-V is a special architecture, which is the latest architecture and the modern version of ARM. So if the ARM architecture has 16 registers, RISC-V has total 32 registers in it. So it will have 32 general purpose registers. It can be referred as X0, X1, X2 up to X31. X0 is hardwired to 0, so its value will always remain 0. whereas X1 works as a link register. So similar to R14, the RISC-V has X1 register, which is called a link register. The ARM architecture only has 3 PSRs and only 1 control register, whereas RISC-V architecture has a large collection of control register as well as the status registers. And the other feature of RISC-V is that it can give you the outputs of 2 registers simultaneously. So that is why it is called the dual read port enabled register file. So its register file is dual read enabled. You have 2 different inputs at which you can give the addresses of 2 different registers. RA and RB will hold the pointer or the register number at which you are supposed to read the data. So you will give RA as, let's suppose, 0 to 32, any number between 0 to 32, 0 to 31, sorry. And in RB, you may give any number from 0 to 31, a 5-bit number over here, 5-bit number over here. It will read the data from the address given by RA and from the address given by RB at the same time, and it will generate the output at A output pin and B output pin simultaneously. So it's a dual read enabled port. Whereas in terms of write operation, it will have only one write enabled. So you will give the value to be written using this input pin, and you will select the register number over here. After selecting the register number and after feeding the value at this pin, you will make a transition from W to WE, and that particular register will be written. So this is how the register file is working in RISC-V core. Whereas in ARM architecture, you can only read one register at a time, and you can only write one register at a time. Any questions so far? किसी को यहाँ तक कोई क्वेश्चन हो? Okay, these were the things we have done in the last lecture. So this was a brief overview of the last lecture. In this particular session, we are going to introduce the processor operating modes or the operation modes. The ARM Cortex-M architecture supports 2 modes of operation. The first mode is called the thread mode. The second is called the handler mode. In these modes, you may either have privileged access or unprivileged access. These are 2 different things. Remember, there are 2 modes of processor architecture. The first mode is called the thread mode. The second is called the handler mode. And within these modes, you may have privileged access to all the registers or unprivileged access to few of the registers. Thread mode is the one in which the processor enters whenever it gets resets or some sort of exception. Whenever an exception is returned, an exception arrived, you processed it, you handled it. The NVIC simply do the important stuff based on the exception number. And when you are returning from the exception, you will return in thread mode. So thread mode will be enabled inside the processor on reset or as a result of an exception return. The code execution can either have privileged access or unprivileged access based on the application program that you are running. Whatever application program you are running in thread mode, you may either have privileged access or unprivileged access. Whereas in handler mode is a special mode in which the processor enters as a result of an exception. Whenever an exception will arrive, then whenever the NVIC will be evoked, the processor will simply go to handler mode. And in the handler mode, you will always have the privileged access. The NVIC enabled handler mode will always have the privileged access. You may update any global variable, you may update any stack, you may update any register, you may read from any register, but you need to perform you need to stop that exception. So the processor will always have privileged mode in handler mode, a privileged access in handler mode, whereas it may have privileged or unprivileged access in thread mode. So thread mode is a common mode. Handler mode is a special mode in which you are currently executing some sort of handler, some sort of interrupt handler. This is a possible state transition diagram. In this possible state transition diagram, whenever the process will get reset, it will always start from thread mode and it will have all the accesses, privileged access. So whenever the process will get started, it will have thread mode as in privileged access level. If you are in thread mode and you have the privileged access, then if an exception is arrived, then based on that exception, you will switch from thread mode to the handler mode. And within the handler mode, you will always have the privileged access. So whenever an exception or interrupt will occur, if you were in thread mode previously, you will always go to handler mode, and in the handler mode you will always have the privileged access. Once you are done with the handler mode, then you may switch back to thread mode again. But if the control bit is zero, so if the control bit 0 is 0, you will come back to the thread mode, but you will have privileged access. And if you have in the privileged access, yaad rakhiyega, in the privileged access, you have the, just give me a second. Sorry. In the privileged access level, you have the access to all registers. So you may update the control register as well. So if you will, in the privileged access level, you will update the control bit 0 to 1, then you will enter into unprivileged or user access level. In user access level, you cannot update control register. So you can come from privileged level to unprivileged level by just writing the bit zeros from 0 to 1. But you cannot go back to privileged access again, because in user access level, you do not have the access to write the control register. So if you are in thread mode and you have the user access or unprivileged access and an exception or interrupt arrived, then based on the exception, you will once again switch to the handler mode. And in handler mode, you will have the privileged access. And after the successful execution of the interrupt handler, you will switch back to the thread mode again. But in this particular fashion, if in handler mode, once again, you have the privileged access. So while coming back, if you will update the control bit 0 to 1 again, then your access level will also be changed to unprivileged and your mode will be changed from handler to thread mode. So there are two different modes called thread mode and the handler mode. And there are two different privilege levels, unprivileged levels and the privileged level. In the privileged level, you will have access to write all possible registers, but in the user level, you will have the access to only a few registers. So you can come back from privileged level to unprivileged level just by writing 1 in the control bit 0. But you cannot go back to privileged level automatically. You will go to the privileged level whenever an exception or interrupt will arrive. अगर प्रोसेस दोबारा रीसेट हो जाएगा या कोई एक्सेप्शन आ जाएगी, only in that way you can go back to the privileged access level. And in general way, whenever the system calls occur and your operating system is doing some system task, then operating system will always be in the privileged access level and it will be using the main stack. So main stack is reserved for the operating system tasks. Whereas the user application, any application, any video game or anything that you are currently using on the application program interface, then you will have unprivileged access and you will be using the process stack. The difference between the stacks, the main stack and the process stack, comes whenever you are using, let's suppose, a user application which has some sort of malware in it. So you have some sort of virus or some sort of any other malware thing in it. Then in the process tag, that malware will simply arrive in that process tag. But if the processor will come to know that this file is bogus or it has a virus, so it will simply truncate the process tag. In this way, the operating system will remain intact. So the difference between these tags comes whenever you are using the user application, and for the user application, you always give it a separate memory. And in that separate memory, the user application will be using the process tag. And if some exception or the virus will come, will attack the program, then the process tag will simply initialize to null again, and you will come back to the operating system privileged access, and the main stack will remain intact. So in this way, the main stack will try to reserve the operating system variables or any function variables, and the user application will have the access to only process tag in unprivileged level. So user application will be using the process tag, and it will have the user access, whereas operating system will be using the main stack, and it will have full access or privileged access. This is a summary of the process operation modes, because the process is controlled by control register. So based on different permutation of the control registers, if the control bit 0 is 0 and control bit 1 is also 0, control bit 1, remember, it was controlling the type of stack you are using, and control bit 0 was controlled from here as well. If the control bit if the control bit 0 is 1, it means you have the user mode. You are at user level, and if this bit 1 is, it means you are using the main stack, and if this bit 1 is 1.
सर आपकी आवाज बहुत कट रही है.
सॉरी, कब से आवाज कट रही है
सर? ये आपके कंट्रोल बिट्स पे जब आप आए, कंट्रोल बिट्स की कॉन्फ़िगरेशन पे जब आप आए तब से पिछली स्लाइड्स
कॉम्बिनेशन से बताया था.
अच्छा, मैं ये चीज दोबारा, ठीक है, मैं दोबारा रिपीट कर देता हूँ. मैं जस्ट इसको समराइज करने के लिए आया था कि controlling the type of stack, 0 means MSP, 1 means PSP, and control bit 0 was 0 means privileged level, 1 means unprivileged level. So based on the permission of these control bits, you can summarize the processor operating modes. Within these processor operating modes, the control register will be controlling the access level and the type of stack. If the control bit 0 is 0 and control bit 1 is also 0, it means you are at privileged 0 and you are using the main stack because of this 0. So for simple application, when you have control bit 0 and control bit 1 both are at 0, then you have the privileged access level and you are using the main stack pointer. If the control bit 0 is still 0, but you have enabled the control bit 1, it means you are still in privileged access level, but now you have switched from MSP to PSP. This 0-0 combination will always be in this particular domain. In the operating system domain, whenever the system call will occur, the operating system will be working in privileged access level and will be using the main stack. So for the operating system domain, this 0-0 combination will always hold. Whereas in a few of the applications, you have given the privileged access level and you are using the main stack, you are using the process stack. So you are in privileged access because of this 0, and you are using the process stack because of this 1, and a few of the user application will run on this combination 0-1. So when a user application program runs in privileged thread mode on top of an embedded operating system, and operating system is currently using main stack in parallel, whereas the user application is running on top of the operating system, and that user application is using the PSP. while MSP is used by the operating system kernel and exception or interrupt handler. So operating system will keep on using the MSP. It will be always be on 0-0 combination. But if the application program is running on top of the embedded operating system, then that user application program will have the privileged level and it will be using the process stack. So 0-1 combination holds for the user application program which are running on top of operating system and they are enjoying the privileged access. If you will set the control bit 0, it means if control bit 0 is 1, your access level has changed. So this is an unprivileged access level or user level, and this 0 means you are using the main stack pointer. This is a highly unlikely combination. If you are at unprivileged level, you will always be using the PSP. So it's an unlikely scenario in which the user application is running in user access level or unprivileged access level and still uses the MSP. It is not possible for all the applications. Actually, it is not possible for any of the application. So in unprivileged access, you will always have the access to PSP, not the MSP. So this is a highly unlikely scenario. And the last possible permutation of these control registered bits is 1-1. In 1-1, you are in unprivileged access level and you are using the process stack register. So in this case, the user application program runs in unprivileged mode. जी कोई आवाज आई है किसी की, कोई क्वेश्चन है? Okay, I guess कोई क्वेश्चन नहीं है. So 1-1 combination means the user application program is running in unprivileged or user mode on top of an embedded system, embedded operating system. The user application will be using the PSP, while once again remember the MSP will always be in used by the operating system kernel, the exception or in the interrupt handlers. So all interrupt handlers, NVIC, exception handlers, and operating system kernel will be using MSP in parallel, whereas the user application will be using the PSP. So user applications variables and the user application function will reside in the PSP section, whereas the operating system will keep on using the MSP. So this 1-1 combination is very common in your basic user applications. This 1-0 combination is highly unlikely. 0-0 combination will be at the operating systems level, whereas 0-1 is an exception in which you have the privileged level at the user application mode. So user application may or may not have the privileged access level, but it will always be using the PSP. Okay, any questions so far? किसी को कोई सवाल यहाँ तक?
सर ये यूजर एप्लीकेशन से ये हमेशा थ्रेड मोड में रन करेंगे?
जी ये थ्रेड मोड में रन करेंगे. जब एक्सेप्शन आएगी ना, एक्सेप्शन हैंडलर जो है वो हैंडलर मोड में सिर्फ रन करेगा. बेसिक एग्जीक्यूशन हमेशा थ्रेड मोड में होगी. कोई और क्वेश्चन किसी को? Okay, so next concept that we will be discussing is called the process interrupt response sequence. Whenever a normal execution is stopped by some hardware fault or some software fault or some power failure, you will always call it as an interrupt or an exception. So the processor response involves the following sequence of operations in case of an interrupt or exception. Interrupt always arrived when a random sequence or a random event is generated while executing your normal program. So you were executing your normal program and something happened at the backside, at the software side or at the hardware side, or a power failure occurred, or a bus is not responding, or some other events has arrived. So that type of event will demand the processor to do some sequence of operations. That sequence of operation includes whenever an event will occur, an interrupt request is generated to the processor. When a particular event will arrive, an interrupt request will be generated. this interrupt request will do some things, and those some things will be discussed in chapter number 9 when we will be discussing the NVIC and NVIC's registers. So the interrupt request will do something to the stack, will do something to the privileged level, will do something to the NVIC registers, but it will cause some sort of action it will do some actions inside the processor core. So interrupt request will be generated. The processor will suspend the current task execution, whichever line it is executing, whatever thing it is doing, whatever results are generating in the ALU, it will simply suspend everything. So it will suspend the current task execution in response to that interrupt and start executing an interrupt service routine. Now, what is this interrupt service routine? As I have said earlier, the ARM processor has given each type of exception or interrupt a number. So based on that number, each type of exception has been given a handler function as well. So if a reset has occurred, the processor startup file has the definition of reset handler. So reset handler will be called. When a hard fault will occur, the hard fault handler is also located in your startup file. So that program will start its execution. So that execution is called interrupt service routine. So based on the exception number, that what type of exception has arrived, it will start the execution of the interrupt service routine to generate the response to that event. So the response to that event will be generated while after the execution of the interrupt service routine. And once the response to the event is completed, you are done with the task, you are done with that exception, the processor will simply resume the execution of the suspended task. So it will once again go back to the thread mode, either in privileged access or user access mode, and then it will resume the execution of the suspended task at where it left. तो जहां से स्टार्ट किया था वहीं से सॉरी जहां पर पॉज किया था वहीं पर वापस आ जाएगा. The very common type of exception response sequence include the processor reset sequence. Resetting is a very common thing. So the processor reset sequence has a very basic type of ISR. In Cortex-M processor, it involves the following sequence of operation on reset. Whenever a processor will get reset after a power failure or you have manually reset it. जी कोई क्वेश्चन है किसी को?
सर एक्सेप्शन कितनी तरह की हो सकती हैं? एक तो ये मैलवेयर अटैक हो गया ना सर, और किस तरह की हो सकती हैं?
एक्सेप्शन इस तरह की हो सकती हैं. एक्सेप्शन में से सबसे पहली एक्सेप्शन तो आती है आपने खुद अगर कोई ट्रिगरिंग इवेंट क्रिएट किया, ओके, अगर कोई सेंसर मुझे इस पिन पर इनपुट देगा तो एक्सेप्शन कॉज कर देना. ठीक है, हम लोग आगे जाके डिस्कस करेंगे कि एक्सेप्शन और पोलिंग में फर्क क्या होता है, लेकिन आमतौर पे प्रोसेसर को कि जब इस पिन पर डेटा आने वाला होगा ना मुझे बता देना, या जब मैंने इस पिन से कोई ना कोई सिग्नल आएगा तो मुझे इन्फॉर्म कर देना, या टाइम इस वैल्यू पे पहुंचेगा तब मुझे इन्फॉर्म कर देना. इस तरह की भी आ सकती हैं. मैं रिपीट करता हूँ, मैं ये कह रहा था कि एक्सेप्शन डिफरेंट टाइप्स की हो सकती हैं. फॉर एग्जांपल एक पिन लेवल पे एक्सेप्शन भी हो सकती है, GPIO लेवल पर, जनरल पर्पस इनपुट आउटपुट पिन जो होती है उस लेवल पे भी एक्सेप्शन हो सकती है. बल्कि मैं एक्सेप्शन की लिस्ट आपको दिखाई देता हूँ एक बार. जस्ट गिव मी अ सेकंड, मैं अपना कील ओपन करके दिखा देता हूँ. स्क्रीन में आपको सिर्फ PDF शो हो रही है.
यस सर.
Let me share the screen again. जी ये विजिबल है सबको?
यस सर.
ओके, ये जो अभी आपके सामने टेबल मैंने शो किया हुआ है ये स्टार्टअप फाइल का टेबल है. In this startup file table, it has a vector table in it. This is called vectors command, and it belongs to vector table. In this vector table, each and every type of exception or interrupt has been given a number. So जो भी exception या interrupt आने वाली होगी उसको एक अदर exception number या interrupt number दिया गया है. For example, the reset handler, the very common and very basic of them. The reset exception has a exception number 0. Similarly, NMI stands for non-maskable interrupts. These are the special type of interrupts that cannot be masked. अगर प्रोसेसर कोई भी काम कर रहा है, इन interrupts को लाजमी हैंडल करना पड़ेगा. The other type of exception is called hard fault, memory management fault, bus fault, usage fault, SPC fault. SPC इसके बारे में हम डिस्कस करेंगे. ये क्लॉक का फॉल्ट होता है. अभी इस टाइम भी ये समझना है इसका. So debugging fault, the SP fault, the cystic fault, and these are the external interrupts. So external interrupts में GPIO stands for general purpose input output pin. So GPIO's general purpose input output pin A handler, B handler, C, ये सारे इनके पोर्ट्स के नाम है. So पोर्ट A पर कोई इंटरप्ट आएगी तो पोर्ट A का हैंडलर कॉल होगा. पोर्ट B पे इंटरप्ट आएगी, पोर्ट B का हैंडलर कॉल होगा. Similarly, at port D, the handler of GPIO port D will be called UART, SSI, I2C, PWM. These are the type of all possible interrupts. So ये सारी possible interrupts हैं. So they are 138 in total. 138 external interrupts and 10 internal exceptions. So ये vector table है complete. जितनी तरह की इंटरप्ट्स आ सकती हैं उन सबको कैटेगराइज किया हुआ है और सबको एक्सेप्शन नंबर दिया हुआ है. सो बेस्ड ऑन दैट एक्सेप्शन नंबर यू विल स्टार्ट एग्जीक्यूटिंग द हैंडलर्स. सो दीज आर द डेफिनेशंस ऑफ दोज हैंडलर्स. ये रीसेट हैंडलर की डेफिनेशन है. ये NMI हैंडलर है. ये हार्ड फॉल्ट हैंडलर है. सो दीज आर द डेफिनेशंस ऑफ ऑल दीज हैंडलर्स. सो स्टार्टअप फाइल में आपके पास वेक्टर टेबल है, आपकी स्टैक की डेफिनेशन है और सारे हैंडलर्स हैं. दीज आर ऑल द पॉसिबल हैंडलर्स. तो जितने 138 हैंडलर्स है उन सबको यहाँ पर उसकी एग्जिस्टेंस या इंस्टेंस क्रिएट की गई हुई है.
सर अगर कोई ऐसी एक्सेप्शन आए कि जो इन 138 में से ना हो,
ऐसा ये बहुत रेयर काम है. अगर ये बहुत रेयर काम है, लेकिन अगर ऐसी एक्सेप्शन आ जाती है तो सिंस उसको प्रोग्राम ही नहीं किया हुआ उसके लिए, तो वो उसको परफॉर्म नहीं कर पाएगा. वो वहाँ पे हैंग हो जाएगा या कोई ना कोई वहीं पर स्टक हो जाएगा, क्योंकि कुछ नहीं कर सकते ना. अब ऐसी एक्सेप्शन कौन सी होगी? ऐसी एक्सेप्शन ये है कि प्रोसेसर हीट अप होकर जल गया, तो वो क्या करेगा बेचारा?
एक्सक्यूज मी सर ये जो आप दिखा रहे हैं एक्सेप्शंस, ये कॉर्टेक्स M3 आर्किटेक्चर की? ये
कॉर्टेक्स M आर्किटेक्चर की, ये जनरल कॉर्टेक्स M आर्किटेक्चर की. M3 में और M4 में कोई ज़्यादा फर्क नहीं है. M4 की भी यही होंगी, बस इसमें M4 की DSP की जो आपके पास आएंगी ना इंस्ट्रक्शंस, उसके हैंडलर्स भी साथ ऐड हो जाएंगे. लेकिन फॉर द टाइम बीइंग ये M3 की है. ठीक है, हम लोग जेनेरिक कॉर्टेक्स M आर्किटेक्चर डिस्कस कर रहे हैं. ये सब में कॉमन है with an exception of some extensions.
Thank you, sir.
Okay, so the first or a very basic type of processor ISR is the reset sequence. The reset sequence is a very common sequence within the Cortex M processor. So it involves only 2 steps. So the Cortex M processor response involves the following sequence of operation on reset. Whenever a processor will get reset, it will perform these 2 tasks at the very starting phase. It will simply go to this address. This is the basic address. It will go to that address. This address in the code memory contains the starting value that is loaded to main stack pointer. It will hold the photocopy of main stack pointer. So this address holds the value of MSB. So whenever the processor gets reset, it does not know what it was doing. It simply has been stuck. कभी भी सो के उठा है, इसको समझ नहीं आ रही, आंखें बंद हैं इसकी बेचारे की. So it will simply go to this address and it will take the MSB from it. MSB की वैल्यू ये ले लेगा and that value will be stored inside R13. So R13 को जब वो वैल्यू मिल जाएगी, so the stack variables will all the variables residing inside the stack you can currently access them automatically. आपको टॉप ऑफ स्टैक मिल गया, अब उसको पॉप करना स्टार्ट करते हैं, वेरिएबल्स की वैल्यूज आना शुरू हो जाएंगी. After doing this first step, reaching at address 0 and then fetching the value that is stored inside this address and then storing that value inside MSB, the first task is done. It will simply go to this as in the code. It will fetch the value that is stored inside this address. That value is a copy of MSB, and that value will be loaded inside main stack pointer. After doing the first step, it will go to the address 0x all zeros 4. So it will reach to this address. Now this address has the value reset vector is contained at this address. This address will have the address to the vector table or reset vector. And the program counter is loaded with this value. Program counter को आप vector table का address बता देंगे. So if you will go to this address contains the address of vector table, and this vector table's address will be loaded inside the program counter. So program counter will simply jump to that, and after reaching that vector table, it will start the execution of reset interrupt service routine. So in reset handler की execution शुरू हो जाएगी program counter के through. So program counter will reach the vector table. It will go to the reset handler, and it will start executing the reset handling, or simply called reset interrupt service routine. Interrupt service routine is also called ISR. So a reset का ISR execution शुरू हो जाएगी. So this is the processor reset sequence, that whenever the Cortex M processor will get reset, it will first go to address all zeros. This address all zeros contains a copy of the MSP. So it will fetch the copy of MSP and will store the result in R30. And after that, it will go to address all zeros 4. This address will hold the value of the vector table's address, and that value will be stored inside the program counter. So the program counter will simply jump to that address. It will fetch the ISR's function and start the execution of interrupt reset ISR. This is the complete processor reset sequence. After the successful execution of processor reset ISR, it will simply go to the value at which the processor was reset. Next discussion is on data path. So the Cortex M architecture or Cortex M3 architecture exclusively has 3-stage pipeline in it. Every instruction, whenever it reaches to the processor, it will be executed in 3 steps or 3 stages. The first stage is called the instruction fetch stage. The second is called instruction decode, and the third is called instruction execution. In the instruction fetch stage, the instruction will be fetched from the instruction memory or from the code memory, and this will be done via program counter. Program counter will be pointing to that particular instruction. Program counter reading the program counter's value, we will go to that instruction, and the processor will fetch that instruction. After fetching that machine instruction, the processor will try to decode it. Decode it in a sense that what is this type of instruction, ये इसमें add करना है, इसमें subtract करना है, इसमें क्या करना है. Control unit will decide the hierarchy to decode that instruction, and after successfully decoding it, the processor will execute that instruction and will store the results back inside the memory or inside the register. So these are the 3 steps in Cortex M3 processor that is used to decode, that is used to fetch, decode, and execute any particular instruction within the processor core. The processor will simply fetch the instruction first. The control unit will try to decode it, and after that, the execution plan will be finalized, and it will be executed with the help of ALU, FPU, and any other particular source residing inside the processor. Now, based on these stages of the instruction sets, you can execute your instance in the form of a pipeline or approach. Within the pipeline approach, this gray area. जी क्या आवाज नहीं आ रही?
इधर अभी थोड़ी देर के लिए सर बिल्कुल आवाज नहीं आई थी, वो थोड़ा सर ठीक
सर यही वाली स्लाइड से आवाज आनी अभी कट गई थी।
हेलो स्टूडेंट्स, आपको आवाज आ रही है मेरी?
यस सर।
यस सर, आ रही है।
सॉरी, कहाँ से आवाज ब्रेक हुई थी वो मुझे बता दीजिएगा, कहाँ से मैंने छोड़ा था।
यही स्लाइड।
Okay, यही slide थी. So we were discussing that we can execute the instruction in a non-pipeline approach, or you may execute it in a pipelined approach. In non-pipelined approach, let's suppose this gray area is the instruction 1 and this white area is instruction 2. So in non-pipeline approach, you will first of all fetch the first instruction, you will decode it, you will execute it, and after successful execution and after storing the result back inside the memory or register, you will fetch the instruction 2 and you will keep on doing these things on instruction 2 as well. Whereas in pipeline approach, the pipeline version is the optimized version of the instruction execution. In this pipeline approach, you will first of all fetch the instruction, you will decode the instruction 1, but while decoding the instruction 1, you will fetch the second instruction using the updated value of program counter and using the bus system, because bus matrix is available when you are in decoding phase. You are decoding, it means the control unit is busy, but the bus system or bus matrix can fetch the next instruction for you. So the processor will be fetching the next instruction in parallel while decoding the first instruction by the control unit. So the control unit will be decoding the first instruction and the processor will be fetching the next instruction, which is instruction 2, using the bus matrix. So the bus matrix will be in use in parallel while decoding. Similarly, if you will try to execute the first instruction, so while executing the first instruction with the help of ALUs and FPUs, the second instruction will start its decoding phase. And in parallel to the decoding, the third instruction will be fetched by the bus matrix. And this sequence will keep on performing until all instruction will be executed successfully. So this type of version is called the pipeline version, or it is also called 3-stage pipeline version. And as you can see from the given example, if you have 4 different instructions and this line is representing 1 clock cycle or 1 unit time, then you can easily calculate how much number of time cycles are required in non-pipeline version as well as in pipeline version. Let's suppose if you have 4 instructions, one instruction is getting executed in 3 clock cycles or 3 unit steps. So the first instruction in non-pipeline form, the first instruction will be executed in 3 unit times. The second instruction will take its own 3 unit times. The third instruction will take its own 3 unit times. And while decoding and executing 4 instructions, you are required 12 unit of time for the complete execution. Whereas in pipeline approach, as you can see, you are doing everything in parallel. So you have done only fetching part in the first unit cycle. In the second unit cycle, you are decoding the first instruction and fetching the second one. So in 2 clock cycles, you are over here. In third clock cycle, your first execution is finished. But after that, each execution will take only 1 clock cycle. So after the 4th clock cycle, your second instruction is done. At your 5th clock cycle, your third instruction is done. And at your 6th clock cycle, all 4 instructions have been executed successfully. So the first instruction will take the same time as that of non-pipeline version. But after that, the optimization starts. So after that, after each clock cycle, the execution of the next instruction will be possible. So this type of hierarchy or this type of execution sequence is called the pipelined approach. The other one is called non-pipelined approach. Is it clear?
सर ये आप कैसे चूज करते हैं कि आप कौन सी अप्रोच यूज
ये
करेंगे
हम
या आप
चूज नहीं
कैसे
करते।
सेट करते हैं?
नहीं, ये हम लोग चूज नहीं करते ना, हम इसको प्रोग्रामिंग में कुछ कर सकते हैं। ये आपका प्रोसेसर जो आर्किटेक्चर है ना, वो आर्किटेक्चर मैन्युफैक्चरर ने ही इस चीज को डिजाइन किया हुआ है। जैसे कॉर्टेक्स M3 जो है वो चलता ही 3 स्टेप पाइपलाइन पे है। इसी तरह जो कॉर्टेक्स A8 आर्किटेक्चर है ना, जो कि अभी सेलफोन्स में आना शुरू हुआ है, वो कॉर्टेक्स A8 आर्किटेक्चर 8 स्टेप पाइपलाइन यूज करता है। सिमिलरली आगे जाके जितने भी इस तरह के प्रोसेसर्स आ रहे हैं वो उतनी स्टेजेस की पाइपलाइन बना के बैठे हुए हैं। सो ये स्टेज पाइपलाइन आर्किटेक्चर डिपेंडेंट या वेंडर डिपेंडेंट है।
ओके सर, थैंक यू।
So this is the complete data path of an ARM based architecture. इस data path की आपको understanding होनी चाहिए because you have already covered the DSD as well. So starting from this particular area, this is the instruction bus, or that is connected to your instruction memory or code memory. This is the instruction decoder. So instruction will be decoded and the value will be stored in the register bank. So the register bank will give you the two operands, operand A and operand B. These two operands will be given to your ALU via some sort of barrel shifter. This barrel shifter is a special hardware device that will be used to shift left or shift right your operand. So those operands which were provided by the register bank, they will be passed through the barrel shifter. If the shift instruction is a part of the current instruction, you will see a few of the assembly instruction also contain the arithmetic plus the shift instruction. So the shift instruction will be done first, then the updated arguments or updated operands will be provided to the ALU. ALU will perform some sort of execution or sort of arithmetic operation. And after the successful arithmetic operations, the results will be stored back inside the register memory or back inside the direct, just in the case of ARM, back inside the register bank. So the ALU's result will be stored inside the register bank. If you want to update it inside the memory, then you will take the value from the register bank. You will write the data to the memory using the data bus. And if you want to read something, then you will take the data from the data bus, you will read it and store it inside the register bank. So this arrow is pointing to the read operation. This arrow is pointing at the right operation. This is the decoding part. This is the register bank. These are the operands. This ALU will perform the arithmetic instructions, arithmetic operations for you. Results will be stored inside the register bank, and these are the things to update your program counter's value. The program counter will get updated to the next possible address. Is it clear?
सर रिपीट कर दो।
Okay, मैं repeat कर देता हूँ. First of all, this is called the instruction memory bus or the code memory bus. The code memory is giving you some instruction. So an instruction has been fed through here. This instruction will be decoded by the control unit. So this is the decoder of that instruction. After decoding it, it will generalize whether it's an arithmetic type of instruction or it's a load store instruction. A load store instruction is the one in which you are supposed to read something from the memory or write something to the memory. Or if it's a simple arithmetic instruction, then the instruction will be given to the register bank. So the register bank will be given the operands of those instructions, and based on the fact if it will be a write type of instruction or store type instruction, then that store type instruction will fetch the data from the register. It will write the memory location at which the data is to be written, and in between there is a bidirectional mux. Bidirectional mux means you can either give input from here or you can either give input from here. So it's a bidirectional mux. If it's a write instruction, the data will be fetched from the register memory and it will be loaded inside the actual memory, the main memory. If it's a read type instruction, then the data will come from the data bus, from the memory. It will be read and stored inside the register. So it's a load. If it's a load type instruction, then data will be loaded inside the register bank. If it's a write type of instruction, yeah, store type of instruction, then the data will be stored inside the memory from the register. And if it's a simple arithmetic instruction, simple register to register instruction, then the operands will be provided by the register bank. These operands A and B are the operands at which the arithmetic operation is needed to be performed. These operands will be given to the ALU. ALU will perform the arithmetic operations on A and B operands, and it will generate some result. And that result will be stored inside the register bank again. So based on that result, it will take some decision whether you want to jump, or if the if condition is true or else condition, else program is to be executed or the loop is to be terminated. So these type of decisions will be taken, and after taking that decision, the program counter will get updated. So this is the updation command of the program counter. Is it clear now? Okay, अगर कोई question नहीं है तो let's switch to the next instruction. Next slide, sorry. Now, in parallel, as we were discussing the ARM architecture, we will also discuss the RISC-V architecture as well. So in RISC-V data path, whereas in ARM data path, there were only 3 stages of the instruction execution. In RISC-V data path, you have 5 stages. The first 3 stages are the common. Instruction fetch is common, instruction decode is common, instruction execute is common. But after the execution, these 4 are the add-ons. The RISC-V processor will do the memory access in the stage number 4, and it will do the register write back in stage number 5. So RISC-V architecture has 5-stage pipeline in it. So it will have 5 stages: instruction fetch, instruction decode, execute, then memory access, and the register write back. And the data path model of the RISC-V will look like this. This is the data.
सॉरी टू इंटरप्ट सर, वो लेक्चर का दूसरा लेक्चर स्टार्ट हो गया, तो वो सर इरफान पूरे 10:50 पे लेक्चर शुरू कर देते हैं.
ओहो, चलिए ठीक है जी, आज के लिए इतना काफ़ी है. हम लोग इंशाल्लाह इस डेटा पाथ से नेक्स्ट लेक्चर को फिर रिज्यूम करेंगे.